Hi everyone, today we'll do the derivatives of products and quotients. Let's start with finding a derivative. Given f of x equals 2x minus 3 times 3x minus 5. We start by expanding the function. This will give us 2x times 3x is 6x squared, 2x times negative 5 is negative 10x, negative 3 times 3x is negative 9x, and then negative 3 times negative 5 is positive 15. We can combine the negative 10 and the negative 9x to get 6x squared minus 19x plus 15. So to get the derivative of a product, we're first having to find the product. Now that we have the product, we can use the power rule. Remember, the 2 is going to come down, so 6 times 2 gives us a derivative of 12x. Negative 19x, well, this is x to the power 1, which means that x will just go away. 15 is a constant, also goes away. So our derivative is 12x minus 19. But let's have a warning and a little comparison. In the derivative of 12x minus 19, I want you to notice that if I just took the derivative of 2x minus 3, I would get 2. And if I just took the derivative of 3x minus 5, I would get 3. If we multiply them together, 2 times 3 equals 6, and I can see that that's not the same thing as our derivative 12x minus 19. So it's important to notice our derivative is not the derivative of the individual factors. We do have to multiply them out to get the answer. So let's do it again. Let's do the derivative of e to the x times the natural log of x. And hopefully you see we can't expand this and we can't separate the factors. So what are we going to do? We're going to need a new rule. So our new rule is called the product rule. So this says if I have a product f times g, to get the derivative, I take the derivative of f, multiply it by g, then I add f times the derivative of g. So I'm doing the derivative of each factor, but one at a time. So we can say this in words as the derivative of the first times the second, plus the first times the derivative of the second. If you have a sheet together where you're keeping track of the rules, right now we have the power rule, we have a constant rule, we have 4 rules that we talked about with e and ln, e to the x, b to the x, ln of x, log base b of x. I would add this to that list. This is an important rule that we're going to use over and over this semester. Also notice, order doesn't matter. I tend to write f prime times g plus f times g prime, but if you decide you're going to do it opposite of that, like fg prime plus f prime g, you will get the same thing because it's addition, but it's only because it's addition that the order doesn't matter when you're doing this product rule derivative. So let's try that. Let's go back to our first example, which we said we know the derivative is going to be 12x minus 19, and let's see how we could do that using the product rule. I'm going to write it a really long way to start. I'm going to make a plan. So my plan is 2x minus 3, I'm going to take the derivative, but I'm going to keep 3x minus 5. Then I'm going to go back to 2x minus 3, and then take the derivative of 3x minus 5. So I'll do one derivative in each one. 2x minus 3, I have the derivative is 2, multiply by 3x minus 5, plus I keep the 2x minus 3, derivative of 3x minus 5 is 3. Let's expand this. 2 times 3x is 6x, 2 times negative 5 is minus 10, plus 2x times 3 is 6x, and then negative 3 times 3 is minus 9. I can combine the 6x and 6x, that gives me 12x. Negative 10 minus 9 is negative 19. Comparing the two, you can see we get the same thing. You do have choices. So if you get this, where it's 2 factors and you can multiply it out, you're welcome to do that. You can multiply first and then take the derivative, but we're going to get to plenty of cases where you have to use the product rule because the terms can't be separated or they're just too complicated to multiply out. So let's try. F of x is 3x squared times natural log of x. These two I can't multiply out, so I'm going to have to use the product rule. Again, I'll do it kind of the long way, make a plan. My plan is first, take the derivative of 3x squared, just bring the natural log of x along, plus, then go back to 3x squared, and let's take the derivative of the natural log of x. So my derivative of 3x squared is 6x. Natural log of x stays the same. Then I keep 3x squared. Hopefully you remember, natural log of x, the derivative is 1 over x. I can simplify this only on this last part, the 3x squared times 1 over x. So I'm going to write f prime of x is equal to 6x, natural log of x, plus 3x squared times 1 over x becomes 3x. This is fine just as it is. If you would like to factor because you notice that there is a 6x and a 3x that they're same, you could do that. So I'll do it just to show you what it looks like, but it's not necessary. 3x and 6x have 3x in common. If I factor that out of the first term, that leaves me with 2 natural log of x. And then 3x divided by 3x is 1. So these two are equal. It's up to you which one you give is the answer, but they would both get full points from me. Let's try f of x is 6x to the 4th times e to the x. Again, I have two factors that can't be combined any other way, so when I go to take the derivative, I'm going to do a piece at a time. So I'm going to start with 6x to the 4th. The derivative is 24x cubed. E to the x stays the same. The second time through, I keep 6x to the 4th, and I take the derivative of e to the x, which is just e to the x. So you see no change between those two terms, between the function and the function's derivative. But that's okay, that's what's supposed to happen. Again, I could simplify this if I wanted to, because we're going to need to as the semester progresses. So I can see there's an e to the x in both, so I'm going to take that e to the x out. I also see x cubed and x to the 4th, so an x cubed can come out. 24 and 6, I can take 6 out. So I'm going to factor out 6x cubed e to the x. 6 goes into 24 4 times. X cubed over x cubed is 1. E to the x over e to the x is 1. Here's my plus sign. 6 divided by 6 is 1. X to the 4th over x cubed gives me x, and the e to the x is out. So this is a reduced form. It means the same thing. It's just a different way to look at the answers. Here's one where we could go either way, so I'm going to do it both ways for you again. So the first way I'm going to do is let's multiply it out. So I'm going to have f of x equals 5x to the 5th. 3 and 2 makes 5. 5 times 4 is 20. X cubed and x is x to the 4th. The derivative. Using the power rule, the 5 comes down. I get 25, x to the 4th. 20 times 4 is 80. I have x cubed, and I'm going to stop there. Just to compare it, let's do the product rule. F prime of x, I would start with the 5x cubed. The derivative is 15x squared. I would keep x squared plus 4x. And then I would go back to 5x cubed. X squared, derivative is 2x. 4x, the derivative is 4. That gives me 2x plus 4. Now to show you these are the same, I need to continue. I need to distribute and gather like terms. So 15x squared times x squared, that's 15x to the 4th. 15x squared times 4x, that gives me 60x cubed. 5x cubed times 2x, that's 10x to the 4th. And then 5x cubed times 4 is 20x cubed. I have an x to the 4th and an x to the 4th, so 15 and 10 gives me 25x to the 4th. I have 60x cubed along with 20x cubed, which gives me 80x cubed. So this shows me that the derivative is the same whether I use the product rule or simplify first and use the power rule. I think this is an also good point to show you that it's up to you which one you do. The product rule is handy when I can't multiply things out or write it a different way. So if it were up to me for this particular problem, I would do it this way. I would first multiply and then take the derivative using the power rule. But if I get something that I can't multiply out and I can't write another way, then I'm going to have to go back to the product rule. The hard part is deciding what you're supposed to do when, but the good part is it shouldn't really matter. You should get the same answer in the end. Let's try 2 to the x times 5x squared minus 3 is f of x. Notice this is 2 to the power x, it is not 2x. Because it's 2 to the power x, I don't want to distribute, I don't want to do anything except go straight to my product rule. 2 to the x, remember when you take the derivative, it's 2 to the x times the natural log of 2. I I keep 5x squared minus 3. Plus, go back to 2 to the x. Then the derivative of 5x squared minus 3 is 10x. I'm going to leave this one just like it is. The 2 to the x is common to both, but I'm not going to bother to factor it out this time. Let's try this. Find the derivative of x over 2x plus 6. And hopefully you think, wait a minute, we need another rule to handle derivatives of quotients. So here's our quotient rule. If I have f divided by g and I want to take the derivative, I get g times f prime minus f times g prime over g squared. You can say this a different way, which is how I tend to say it. The part that's on top I call high, the part that's on bottom I call low. So high is the numerator, low is the denominator. Then the derivative is low d high minus high d low over low low. D high means derivative of high, so the derivative of the top. D low means the derivative of the bottom. I just find this one's easy. This is how I was taught to do it back when I took calculus, and it kind of hung out with me, and I think students like it because it's something you can easily say. You can say low d high minus high d low over low low. Low low on the bottom means the bottom squared, just like it says g squared in this other formula. Low low just sounds cuter. That's the only reason we're saying low low instead of low squared. It just kind of rolls off the tongue better. So let's go back to our x over 2x plus 6. And remember that was f of x. And let's try this low d high. So f prime of x. Low, put in parentheses, 2x plus 6. D high, derivative of x is 1. Minus high, which is x. D low, derivative is 2, all over the bottom squared. With the quotient rule, it's really important to see this negative sign means order is important. If you switch how you put these terms into the numerator, you're going to get a different answer. The sign will be different, so really pay attention to which one goes first when you use the quotient rule. We can definitely simplify this. So 2x plus 6 times 1 is 2x plus 6. Then negative x2 is 2x, and this is all over 2x plus 6 squared. Let's put that square down there. 2x plus 6 minus 2x, the 2x goes away. I end up with 6 over 2x plus 6 squared. Notice I didn't cancel anything out earlier. You really want to simplify the numerator, simplify the denominator. There's not going to be a time where we are going to use this square as far as multiplying it out or making it bigger. So don't think about we're going to have to square this binomial. We're not going to do that. We want to leave it in factored form. Let's do some more of those. Here I have 6x plus 3 over 5x plus 9. This is going to be equal to f of x. I'm ready for the derivative, so I start low, 5x plus 9. I want to put these in parentheses because there will be a distribution to do, so you want to make sure you use both of the terms in the distribution. So there's my low, d high, derivative of 6x plus 3 is 6, minus high, 6x plus 3. Derivative of low, 5x plus 9 is just 5. And then all over the bottom squared. Okay. I have heard from students over the years that they're going to cancel like this, and I want to say absolutely not. Like, you can't do that. So let's get rid of that. Both of these terms are being divided by 5x plus 9 squared, so if you only cancel on the left side, the thing on the right didn't get divided, so you don't want to do that. What we want to do instead is distribute the 6. So 6 times 5x is 30x. 6 times 9 is 54. Really important that you notice this is a minus sign in between, so I'm going to think of multiplying by negative 5. So negative 5 times 6 is minus 30x, and negative 5 times 3 is negative 15, and then again over the denominator squared. Now I can cancel 30x with negative 30x. Then I can put together 54 with 15. My answer is 39 over 5x plus 9 squared. Let me change the notation on this one. I'll call it y. I have 8x squared over 2x plus 1 equals y. Then y prime is low, 2x plus 1. D high, derivative of 8x squared is 16x. minus high, 8x squared, d low is 2, and then all over the bottom squared. Now I'm going to again distribute, so I need to multiply the 16x times the 2x and the 1, so 16x times 2x is 32x squared. 16x times 1 is 16x. Remember, you have a negative, so I have minus 8x squared times 2 is 16x squared over 2x plus 1 squared. I can combine like terms. 32x squared minus 16x squared gives me 16x squared minus 16x over 2x plus 1 squared. Now this is fine. You can leave it like this. If you wanted to, you could factor out a 16x, which would give you x minus 1. This is not necessary, but I want you to see it just as a here's what's going to come later. Eventually we're going to want to factor these, set them equal to 0, but for now I'm just happy to teach you this new rule, that is the quotient rule. Let's again use y, so I have y equals 4x over e to the x plus 9. Y prime will be low e to the x plus 9. D high is 4. So low d high minus high 4x, d low, derivative of e to the x plus 9 is simply e to the x. Remember, e to the x doesn't change. 9 is a constant, so constants have a derivative of 0. On the bottom, we're dividing by e to the x plus 9 squared. So here I have 4 derivatives, and my goal here is for you to stop me. Stop the recording, try these 4, simplify them, see what you can do with them, and then check your answer with me to see how you did. It's important that you see, when do I do what? So when do I do the product rule? When do I do the quotient rule? When do I try to simplify before I do anything? So try these 4, then push play, start it back up, and see how you did. The first one is f of x equals 9x cubed times the natural log of x. I think saying the words aloud or saying them in your head helps you decide what to do. So I said 9x cubed times. As soon as I hear times, I think that's the product rule. Product rule, f prime of x, says 9x cubed, the derivative is 27x squared, keep the natural log of x, then plus, go back to 9x cubed, derivative of natural log of x is 1 over x. The 27x squared, natural log of x is fine. 9x cubed times 1 over x becomes 9x squared. I'm perfectly okay with you leaving it this way, or if you wanted to, you could factor out a 9x squared. You would get 3 natural log of x plus 1. The second one says g of x is the natural log of x over x. So again, I'm looking for what are those key words? Well, I'm a natural log of x over x or natural log of x divided by x. That says quotient, do the quotient rule. So quotient rule starts low. D high, ln of x, the derivative is 1 over x, minus high, natural log of x, derivative of x is 1, all over the bottom squared. X times 1 over x is 1, minus, I have the natural log of x, over x squared. The third one, I have 2x times 5 to the x. Again, 2x times. Time says product rule. So I start out, derivative of 2x is 2. I keep 5 to the x, plus, go back to 2x. Derivative of 5 to the x is 5 to the x, times the natural log of 5. So you have to remember, when the base is different than e, you have to attach the natural log of the base. You can look at it and see there are some similarities. So if you wanted to factor out a 2 from each one, factor out a 5 to the x in each one, you can, or you can leave it like it is. I'll show you the factored form in case you want to see it. So if the 2 times 5 to the x comes out, well, 2 times 5 to the x divided by 2 times 5 to the x is 1. On the right side, I still have an x, and I still have the natural log of 5. I also want you to notice I did not multiply 2 times 5. You can't do that. Remember, order of operations are parentheses exponents. So this exponent of x attached to the 5 comes way before the multiplying by 2 does. This is not 2.5, it's 2 times 5. So I have 2 times 5 to the x, parentheses 1 plus x natural log of 5, or you could leave it as 2 times 5 to the x plus 2x times 5 to the x natural log of 5. The fourth one says x squared plus 4x divided by x. So you could do the quotient rule here, but I'm not going to. What I'm going to do instead is notice this x on the bottom is a monomial, and I could divide. X squared over x is x. 4x over x is 4. So I could simplify it before I take the derivative. That way y prime is 1. What you're looking for is, could I rewrite it before I do the derivative? If you did use the quotient rule, you would have had low, which is x, d high, 2x plus 4, minus high, x squared plus 4x, d low was 1 over x squared. Then you would multiply out. 2x times x is 2x squared, plus 4 times x is 4x, minus x squared minus 4x all over x squared. The 4x would cancel the negative 4x. 2x squared minus x squared would give you x squared. X squared over x squared would just be 1. So in the end, we have the same answer. It's just the amount of work that we had to do. I know if you're like me, you don't want to do extra work if you don't have to, so I really do encourage you to look at it, see if you can simplify it all, and if you can, do that before you go after the derivative. Given f of x is 7x over x squared plus 3, this time I want to find the values of x for which f prime of x is equal to 0. We'll start by finding f prime of x. F prime of x will be low, x squared plus 3, d high, which is 7, minus high, 7x, d low, we had x squared plus 3, derivative is 2x, all over the denominator squared. When we multiply that out, 7 times x squared is 7x squared, 7 times 3 is 21, 2x times 7x gives me 14x squared, and see that that was subtracted, all over the bottom squared. 7x squared minus 14x squared gives me negative 7x squared plus 21. That's over x squared plus 3 squared. When we're trying to find the place where the derivative is equal to 0, I only need to look at the numerator, because the only time a fraction can be 0 is if the numerator is 0. So we're going to take our negative 7x squared plus 21, set it equal to 0. That'll say negative 7x squared equals negative 21. Divide by negative 7x squared is 3. We're going to take the square root, take the square root. That says x is equal to plus or minus the square root of 3. I don't need to do anything further than that. The only thing I had to find were the values for where f prime of x equals 0. That's what we found. Here's our last question for today, and it's looking at an application, and it has 3 parts to it. So we're going to start with the number of shirts x that can be sold per week at a price p in dollars can be modeled by the function x equals 9,500 over 0.35p plus 1, where x is between 10 and 100. So the idea was maybe they can only make 100 shirts a week, and they have to make at least 10 per week. I've graphed it already to give you that idea of what's happening. We'll start by finding the derivative dx dp. So we had x is 9,500 over 0.35 p plus 1, and we want to find dx dp. What does this say? It says we're finding the derivative of x with respect to p. So in this case, p is the independent variable and x is the dependent variable. That makes sense in the real world. The price determines how many items sell. So if the price changes, the number we sell changes. We have a quotient, so we're going to do the quotient rule. Let's start with low. Low is 0.35p plus 1. Then we do d high. Well, this one's really important that you stop and look at it. The top, 9,500, is a constant. Derivative of a constant is 0. Not 1, put in 0. So low d high minus high, 9,500. D low, 0.35p is 0.35. and the 1 goes away, and this goes all over the bottom squared. Okay. So this 0 times the 0.35 plus 1 just means that's gone. We can also multiply 9,500 times 0.35. So now I see dx dp equals negative 3,325 over 0.35 p plus 1 squared. The negative shows me that this is decreasing. If we go back to our graph, we can also see that decreasing, right? So it's changing. As p goes up, x is going down. Part B says find the demand and instantaneous rate of change of demand with respect to price when the price is 15, and then write a brief interpretation of these results. In the demand, when the price is 15, we're going to have x is equal to 9,500 over 0.35 times 15 plus 1. It might help to put parentheses around the denominator to make sure it's going to multiply 0.35 times 15 and add 1 before it does the division. This gives 1,520. So this says when the price is $15 per shirt, 1,520 shirts will sell. Right, we're also supposed to find the instantaneous rate of change of the demand. So remember, we just found dx dp to be equal to negative 3,325 over 0.35 p plus 1 squared. What do we want to do? We want to put in the value of 15. So our dx dp is going to be negative 3,325 over 0.35 times 15 plus 1 squared. I got negative 85.12. Okay, what does this say? Well, this says if you increase the price from 15 to 16, I expect the number of shirts to sell to reduce by about 85. Part C, use the results from Part B to estimate the demand when the price is $16. At 15, the demand was 1,520, but the instantaneous rate of change was about 85. So when we put those two things together, we can see that the demand will drop to 1,435 if the price increases from $15 to $16.